A simple resistor behaves exactly as circuit theory predicts. But at high frequencies, even a short piece of wire can become part of the circuit itself. So when does a circuit stop behaving like a collection of components and start behaving like an electromagnetic system? Most introductory circuit analysis is based on the lumped element model. In this approach, components such as resistors, capacitors, and inductors are assumed to exist at specific locations, while the wires connecting them are considered ideal and have no significant effect on circuit behavior. This assumption greatly simplifies analysis and makes circuit theory practical for everyday engineering work. The lumped model works because electrical signals require time to travel through physical space. When circuit dimensions are much smaller than the signal wavelength, all parts of the circuit can be assumed to respond almost simultaneously. Under these conditions, voltage and current can be treated as concentrated at individual components rather than spread throughout the structure. For low-frequency circuits and small electronic systems, this approximation is extremely accurate. Most power supplies, audio circuits, and basic electronic devices can be analyzed successfully using lumped circuit models without needing to consider electromagnetic wave propagation. A distributed system is fundamentally different because voltage and current are no longer confined to individual components. Instead, electrical quantities vary continuously along the physical structure. In these systems, the dimensions of conductors become comparable to the signal wavelength, making propagation effects impossible to ignore. Transmission lines are one of the most common examples of distributed systems. Rather than representing a cable as a simple wire, engineers model it as a continuous distribution of resistance, inductance, capacitance, and conductance along its entire length. This allows accurate prediction of reflections, delays, and wave behavior. As frequency increases, more systems begin to exhibit distributed behavior. Circuits that appear simple at low frequencies may require completely different analysis methods at RF and microwave frequencies because signal propagation becomes a dominant factor. The key factor determining whether a system is lumped or distributed is the relationship between physical size and wavelength. If the circuit dimensions are much smaller than the wavelength, the lumped approximation remains valid. If not, propagation effects become important and distributed models are required. For example, a 10-centimeter wire is insignificant in a low-frequency power circuit operating at 50 Hz. However, at several gigahertz, that same wire may represent a substantial fraction of a wavelength and strongly influence circuit performance. The physical geometry suddenly becomes part of the electrical design. This transition is one of the most important concepts in RF engineering. Engineers must constantly evaluate whether traditional circuit models remain valid or whether electromagnetic wave behavior must be considered explicitly. In practical electronics, engineers often begin with lumped models because they are simpler and computationally efficient. These models provide valuable insight during initial design stages and remain accurate for many applications where wavelengths are large compared to circuit dimensions. As operating frequency increases, engineers gradually introduce distributed models. Transmission lines, printed circuit board traces, connectors, and even component leads may need to be analyzed using electromagnetic principles rather than simple circuit approximations. This shift is particularly important in RF, microwave, and high-speed digital systems. Modern engineering tools frequently combine both approaches. Designers may analyze some portions of a system using conventional circuit theory while modeling other sections as distributed structures. Choosing the correct model is an essential engineering skill. Understanding lumped versus distributed systems is one of the first major steps toward RF engineering. In low-frequency electronics, wires are often treated as ideal connections. In RF systems, those same wires may act as transmission lines, antennas, resonators, or sources of unwanted signal reflections. Many RF concepts such as impedance matching, standing waves, propagation delay, and antenna behavior arise directly from distributed effects. Engineers who ignore these effects often discover that circuits behave very differently from their expectations when frequency increases. This is why RF engineering requires both circuit theory and electromagnetic theory. Lumped models provide the foundation, while distributed models explain what happens when signals begin interacting with physical space itself. So today, we learned that lumped systems assume electrical behavior is concentrated within individual components, while distributed systems recognize that voltage and current can vary continuously throughout a physical structure. This distinction becomes increasingly important as frequency rises and wavelengths become comparable to circuit dimensions. In the next lesson, we'll explore linear versus non-linear circuits and learn why some circuits respond proportionally to inputs while others create entirely new behaviors. If you found this useful, like the video, subscribe, and follow for the next lesson.